suppose instead of different cells, suppose if you take only two cells whose EMF is E1 and internal resistance R1, and one more is E2 and internal resistance of the cell is R2. If these two are connected in parallel like this, and this is the path in which this current can go. Here in this case, the current given by the first cell, let us say this is I1. Current given by second cell is I2. The total current is I. So how to find the effective EMF and effective internal resistance of this combination when two cells connected in parallel? We know that the total current I is given by I1 plus I2. This I is given by E equivalent by R equivalent. Why? Because we are not showing any external resistance here, only for this circuit. Now this will become E1 by R1 plus this is E2 by R2. If you take LCM here, this will become R1 R2. This is E1 R2 plus E2 R1. This is E equivalent by R equivalent. So the effective EMF of this combination or equivalent of EMF of this combination is given by E equivalent is equal E1 R2 plus E2 R1 by R1 R2 into this R equivalent. What is R equivalent here? We know that these two are connected in parallel. The R equivalent in this combination is given by parallel combination R1 R2 by R1 plus R2. Now in place of R equivalent, let me substitute this one. This is E1 R2 plus E2 R1 by R1 into R2 into this is R1 R2 by R1 plus R2. This and this get cancelled. So what is the effective EMF of this combination? The effective EMF of this combination E equivalent is given by E1 R2 plus E2 R1 by R1 plus R2. But you can see this here, the positive terminal of the first cell is connected to the positive terminal of the second cell, and these two are connected to the same point. That means both are giving current in the same direction. So these cells are said to be connected in same sense. Suppose if the cells are connected in reverse sense, so this is E1 with internal resistance R1, but this is E2 with internal resistance R2, and these two connected in parallel like this. So in this case what happens? The first one will give the current here I1 and the total current, let us say I. So from this I1 current, some current is going here. The remaining current will be, let us say this is I2 which is entering into this one. What we can say, the incoming current is I1, the outgoing currents are I and I2. So I can write I1 is equal I plus I2, or I is equal to I1 minus I2. This current is the main current coming from this battery E1 and the current that is entering into this one. Here the condition is E1 greater than E2, then only this current is positive, this current will be into this one. Suppose E2 greater than E1, then this will be I2, this is I, this is I1. Now in this case I am going to use the same method here. E equivalent by R equivalent is equal E1 by R1 minus E2 by R2. If you take LCM, this will become R1 R2 by E1 R2 minus E2 R1. So what is E equivalent? This will become E1 R2 minus E2 R1 by R1 R2 into this R equivalent. This is R1 R2 by R1 plus R2. You can cancel this one. So finally the equivalent EMF of this combination is given by E equivalent E1 R2 minus, this is the only difference between this combination and this combination. If cells are connected in same sense, if cells are connected in same sense, then this will be positive. If cells are connected in opposite polarity or in opposite sense, then this will become minus of E2 R1 by R1 plus R2. Never use minus here because resistance cannot be negative at all. Resistance is always positive. Now what is R equivalent for this combination? The effective resistance, whether these are connected in same sense or in a reverse polarity, reverse sense, R equivalent remains as R1 R2 by R1 plus R2. Heating effect. Consider a resistor of resistance R which is connected to a battery. That means the potential difference between the two ends of this one, let us say this is V. So a PD of a potential V is applied between the two ends of this resistor. Then let us say this is at high potential V and low potential, let us say 0. So the potential difference between the two ends is equal to V minus 0, which is equal to V. Whenever there is a potential difference between the two ends of resistor, a current will flow through this one. The current that is passing through this one is I. So whenever a PD of potential V is applied between two ends of a resistor, then an electric field will be produced. Why? Because whenever there is a difference in the potential, so electric field will be produced from high potential to low potential. So electric field, in the direction of electric field, potential decreases. So what is the direction of electric field here? This is the direction of electric field. So this electric field due to this electric field, the charge will flow from high potential to low potential. We know that in an electric field, positive charge always moves from high potential to low potential. A charge will flow in a given time. That rate of flow of charge through this resistor, we call it as a current. So electric field will do some work to move the charge. To move this charge is nothing but free electrons. So what is the work done by this electric field? This is nothing but potential difference into the charge that is moving here. So W is equal. So what is the potential difference between the two ends of this one? So this I am writing delta V, which is equal to V minus 0, which is equal to V. So this is V into the charge that is flowing here. But we know that this is the electric field is doing some work within some time. So in a given time t. So I can write I is equal to Q by T. In place of Q, I can write IT. So the work done is given by V into IT. Work done is equal to V is equal to IR into IT. So W can be given as I square RT. So this was first observed by Joule. That's why it is called Joule's heating effect. So in this, whatever the work that is done by this electric field will be stored as thermal energy. This will be stored as work done will be stored as thermal energy. So now you can write this thermal energy H is equal to I square RT, because work done will be stored as energy, heat energy. So H is equal to I square RT. What is this H? H is the heat energy produced, heat energy dissipated in that resistor. Dissipated. H is equal to I square RT. This is also called Joule's law of heating effect. So from this we can write H directly proportional to I square, H directly proportional to R, H directly proportional to T. So the Joule's heat, this heat is also known as Joule's heat produced in a resistor, is directly proportional to square of the current if resistance and time are kept constant, if these two are constant. Similarly, the second law states that the quantity of heat produced in a resistor is directly proportional to the resistance of that resistor if the current and time are kept constant. Similarly, third one, the quantity of heat produced in a resistor is directly proportional to the time of flow of current if the current and resistance are kept constant. So from this single equation we can give the first law, second law, third law of heating effect. If you want to find out the heat in joules, you can use this formula, H is equal to I square RT. Why? Because I is the current in amperes, R resistance in ohms, time in seconds. So if you multiply this, you will get this heat energy in joules only. But in general, heat is measured in calories. That's why you can write this equation as H is equal to I square RT by J. If you write this one, then you will get this in calories. If you know the heat energy produced in joules, just divide with J, you will get in calories. Now, the same expression H is equal to I square RT can also be written as here H is equal to I square RT can also be written as. So some more equations. So here what we can write, this is equal to VQ because work done is equal to heat energy. So in some problems they may give the potential difference of the two ends of the resistor and the amount of heat flowing. So H is equal to I square RT is equal to VQ is equal to VIT is equal to this VIT can be written as IR into IT, then you will get I square RT. Already I wrote this I square RT, but you can write V into I can be written as V by R from Ohm's law into T. So this is V square by RT. So these are the different equations that can be used to find out the amount of heat produced in a resistor when a current is flowing through this one. Now, sometimes they may ask you to find out the electric power generated here. Now, by using this Joule's heating effect, if you take the electric iron box uses this principle only. Whenever the current is passing through the resistor, it can produce a lot of heat energy. How to increase this heat energy? Either by sending high current or by using a resistor of high resistance. So electric iron works on this principle. It produces heat whenever some current is passing through this one. Similarly, the electric bulb which is giving some heat energy, and electric geyser is also working on this same principle. So these are some of the devices that works on the principle of Joule's heating effect. Now, what is the power developed there? Power is the rate of doing work. So here I am going to write power P is equal to work done by time. We have different formulas to find out the work. We have 4 different formulas here. So I can write this as I square RT by T cancel. The first one I square R. This is the electric power. Power consumed by resistor. Similarly, one more expression VQ by T. VQ is the work done by T, but Q by T is current, so this is VI. This is also electric power consumed. One more expression VIT by T. VIT by T. TT cancel. So here also I am going to get the same expression VI. And one more equation V square by RT. So I am going to write, instead of this I am going to write here V is equal to work done V square T by R by TT cancel V square by R. So these are the different expressions that can be used to find out the power. In general, we use either R square R or V square by R in a circuit. But if only voltage and current is given, just a product of voltage and current or potential into current will give the electric power. Maximum power theorem. We know that the power is given by the product of current into voltage, which is can also be written as V is equal to IR. We can write I square R are also equal to V square by R. This is the power consumed by a resistor. Now, if you take a simple DC circuit, direct current circuit, so here I am going to take a small battery of EMF E with interrelations R connected to an external resistor of resistance capital R. Now, in this circuit, we know that current will come from this positive terminal of the battery, passes through this resistor and enters into this one into the negative terminal. So, when the key is closed here, let us say there is a key here, if this key is closed, now current will flow from anode to cathode outside and cathode to anode inside this one. Now, what is the amount of current through this one? The amount of current passing through this circuit is given by I is equal to net to EMF by the total resistance of this circuit, which is equal to capital R plus small r. So, this is the current. Now, what is the potential difference between the two ends of this resistor? The PD across R is given by V is equal to I into capital R. So, V is equal to I is this one, capital E by capital R plus small r into capital R. So, this is the potential difference between the two ends of this resistor. What is the power consumed by this resistor? Now, the power consumed by the resistor P is given by, it is the product of I square into R, product of voltage into current, product of V square by R, anyone you can write. If you take this one, product of voltage V by E by capital R plus small r into R into current E by capital R plus small r directly we can write I square R. What is the current here? This is E by capital R plus small r. So, I square can be written as E by capital R plus small r whole square into R. This is the power. But this is about maximum power theorem. So, when the power consumed by the resistor will be maximum. So, we are going to find out the maximum power here. For maximum power, actual power formula P is equal to, here I am writing E square into R by R plus small r whole square. This is the power. When this power may be maximum. For the power to be maximum, the denominator should be minimum. So, what I am going to write, for maximum power, R plus small r whole square should be minimum. If the denominator is minimum, the power consumed by the resistance will be maximum. Why? Because this EMF of cell is constant and capital R we are finding this with respect to capital R only. At what value of capital R power will be maximum? So, what I am going to write, if any function is maximum, its derivative must be equal to 0. So, I am going to use that concept. If P is maximum, then derivative of P power with respect to that resistor, for what value of R power is maximum? That is the question. For what value of capital R, the power through this power consumed by the resistor is maximum. So, differentiate power with respect to that R, and if as power is maximum, already we studied in mathematics that maxima minima chapter, whenever a function is maximum, its derivative must be equal to 0. Here, derivative of power with respect to that R is 0. So, this I am going to take it as 0. So, now I am going to write d by dr of, what is this power? Power formula E square R by R plus small r whole square. So, this is P by dr. So, let me write P in black color only. This is E square R by capital R plus small r whole square must be equal to 0. So, derivative of power with respect to the resistance is 0, because we are finding this resistance with respect to this capital R value when the power is maximum. So, now this is in the form of U by V. So, we can write V into derivative of, here while differentiating this one, as E square is constant. So, let me write E square outside only. So, this is in the U by V formula. So, E is a constant, bring it outside. So, V into derivative of R with respect to R is equal to 1 minus, second, U into derivative of this denominator, that is this is in the form of x power n. So, n into x power n minus 1, 2 minus 1, this is 1 by V square, that formula, we know this formula, d by dx of uv is equal to v into u dash minus u into v dash by v square. So denominator square, already denominator is r plus capital R plus small r whole square, whole power square. So this become r plus r whole power 4. This must be equal to 0. By cross multiplication, we know that this minus this by something is 0, because this into this will be 0. So we can write capital R plus small r whole square minus 2r into capital R plus small r is equal to, by cross multiplication, 0. So from this we can write capital R plus small r, capital R plus small r whole square is equal 2r into capital R plus small r. You can cancel this and this. Capital R plus small r is equal to 2r. Small r is equal to 2r minus r. So capital R is equal to small r. So when the power through a circuit is maximum, the power consumed by resistor is maximum if the external resistance is exactly equal to the internal resistance. So that is the final conclusion. Power consumed by a resistor is maximum if the external resistance is equal to the internal resistance. If the external resistance is equal to internal resistance. So this is how we can prove this maximum power theorem. Once again, the same expression without using this derivation or differentiation method also, we can prove that the power consumed by resistance is maximum if capital R is equal to small r. So how to find that value? So I am going to take the same value here, which is P is equal to E square R by capital R plus small r whole square. In the second method, without using the differentiation, so I am going to use the same formula. Power is equal to E square R by R plus small r whole square. Those who are strong in differentiation can use this method. If you are weak in differentiation, then you can use this method. So as the power is a maximum, this denominator should become minimum. Whenever the denominator is minimum, so let me use this one, E square R by, this denominator can be written as root R plus root small r whole square. See the difference here. I am writing r as root r whole square. Square and root get cancelled, get r only. Root and square cancel, this one. So this can be written as E square by r by, this is in the form of, you can write this as root r plus root small r whole square. You can write the same thing like this also. But you will get what is this root r plus root small r whole square. Root r whole square will be r, root small r whole square will be small r plus 2 root r root small r. So if you expand this binomial expansion by using the binomial theorem, if you expand you will get this one. But I want only this capital R plus small r only. This is an extra term. So I can write 2 root capital R root small r. So you can use like this, or the same can also be written if you write this minus here and you can make this plus. Why? Because if you expand this one, plus capital R plus small r minus 2 capital R small r. For this if you add plus root capital R small r, these two get cancelled, you will get you will be left with capital R plus small r only. So the power equation is E square R. You can write like this or you can write this one also. So this can be written as E square by R. What is the denominator now? This is root capital R minus root small r whole square plus 2 root capital R small r. This is the power consumed. For the power to be maximum, the condition is the denominator should be minimum. So what is the minimum value here? When it can be minimum? 2 into root capital R small r cannot be minimum. This is the product, but you can see this is a subtraction here. This can be minimum. What is the minimum value of this one? We can write the minimum value of this one as it cannot be negative. Resistance cannot be negative at all. And once again, this is a square here. So the minimum value of this one must be equal to 0 only. It cannot be negative. Resistance cannot be negative at all. So what we can write? This minus this must be equal to 0. That is the minimum value. So from this we can write root r is equal to root small r or capital R is equal to small r. So this is how we can prove the maximum power theorem. So this is by using differentiation where we got capital R is equal to small r. So power consumed by resistor is maximum if external resistance is equal to internal resistance. Whereas if the external resistance is equal to internal resistance, then also power consumed will be maximum. This is by using algebra and this is by using calculus. Mixed grouping of cells. Here I have connected so many cells like this. Here all are similar or identical cells having EMF small e each and internal resistance small r each. Let us say there are n cells in this combination. So in the first row we have n cells in series. Similarly, this is the first row, second row, and like that we have m rows. So what are the total number of cells in this combination? The total number of cells is given by, in each row we have n cells and there are m rows. So this is n into m. So these are the total number of cells in this mixed grouping of cells. That means here some cells are connected in series and similar cells are connected in parallel. Similar branches are connected in parallel. So that's why it is called a mixed grouping of cells. So what is the net EMF in the first row? So as there are similar cells, E plus E plus E plus and up to N, this will become NE. And what is the next EMF here? NE, NE, NE. So each and every branch has equal EMF. So equivalent EMF of the combination, which is equal to NE. This is NE. Similarly, what is the equivalent internal resistance of this combination? Which is given by, in each row we have R plus R plus R NR, and these are NR, 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 NR by M rows. This is NR by M. Now, what is the main current that is coming from this one? The current coming from this battery, because combination of cells in series and parallel, either in series, is known as a battery. So from this battery, let the current coming from is I. So main current is given by I is equal to net EMF by net resistance, that is NE by NR by M plus capital R. So this is the total current that is coming from this battery. Now, when the current through this circuit is maximum, current is maximum only if the denominator is minimum. From the maximum power theorem we can say the external resistance must be equal to internal resistance here. But here, which resistance we have to consider? Internal resistance means this is the net to internal resistance. So we can write the external resistance is capital R. The total or effective internal resistance of the combination is given by NR by M. So this is the condition where the resistance will be that minimum and the current will be maximum. For getting maximum current in the circuit, the external resistance must be equal to the effective internal resistance of this mixed grouping of cells. The maximum current. So here if we take this current I, this is NE by NR plus if you take LCM, this will become RM into M. So this is the current that is passing through this one. So here for the current maximum, now we got a numerator and this is the denominator. Here also you can see NR is equal to RM or R is equal to NR by M. So this is what we got. The same thing as I explained earlier, this can be written as MNE by, this can be written as root to NR minus root to RM whole square. If you expand this one, you will get NR plus RM minus 2 NR RM plus 2 NR RM. So these two denominators are same now. Now the minimum value of this one will be 0. So what is the maximum current that is passing through this circuit? If it is 0, then the current will become MNE by 2 root R into small r M into N. So this is the maximum current that is passing through this circuit. So to find out the maximum current, once again you can write this M and root M cancel, N and root M cancel. The maximum current through this circuit is given by root to Mn into E by 2 root capital R small r. This is the maximum current that is passing through this one. Whenever the current is maximum, the power consumed also maximum, which is equal to I square R. You can write, if you square this one, you will get Mn E square by 4 capital R small r into the resistance, because power is equal to I square R, power consumed. So this is I square value R. This R and R get cancelled. So what is the maximum power consumed by this mixed grouping of cells? The maximum power consumed is given by Mn E square by 4 small r. So this is the maximum power consumed by the external resistance in this combination. Now the maximum power, and if you know the EMF of one cell and the internal resistance of this one, if you know E value, R value, you can find the total number of cells that are used in this circuit. Why? Because the total number of cells used in this one is N into M. So how to find total number of cells? This is M into N is equal 4PR by E square is the formula to find out the total number of cells. Topic is about electric bulb. So this is a bulb with P0 and V0, where P0 is the rated power. So this is called rated power, and V0 is called rated voltage. So the values that are printed on the surface of a bulb are called rated power and rated voltage. Generally, the power consumed by a bulb may vary from the rated value. So it may be different from the rated values. Let us say a bulb is given as a 100 watts bulb. This is the power 220 volts. Here the bulb may consume 160 volts or maybe 240 volts. It may be used on 120 volts supply or 200 volts supply or 240 volts supply. When the input voltage is applied voltage is different from the rated voltage, the performance of the bulb will change. Similarly, whenever the rated voltage or the input voltage changes than the rated voltage, the power consumed by this bulb may change. Because of this, the brightness given by this bulb will be different. So generally we know that the power consumed by a bulb, power consumed is given by P is equal to V square by R. This V is not the rated voltage. This V is the applied voltage between these two terminals by R. Let us say if you know the power consumed by this one, if the resistance of a bulb is less, power consumed will be more, or if the power consumed is less, resistance of the bulb will be more. So in general, as we can say that bulb with more rated power, let us say applied voltage and the rated voltage are same, then you can write this as V0 and this power will be P0. So for this voltage, power consumed is this much only. So when the applied voltage is exactly equal to the rated voltage, the power consumed will be exactly equal to the rated power. Then this R value we can write, the bulb with more rated power will have less resistance. If you connect two or more bulbs either in series or in parallel, once again we need to change this statement. So what is that statement? Let me check it. Now, bulbs connected in series. Here I am going to connect two bulbs. This is a first bulb having power P1. This is second bulb having power P2. Now, as these two are connected in series to the same voltage source, here the same amount of current will flow. So whenever bulbs are connected in series, I is same in both bulbs. So same current will flow through these two bulbs. So from this what we can write? What is the voltage across the first bulb and what is the voltage across the second bulb? We know that according to Ohm's law, V is equal to IR, as I is same. The voltage consumed by the bulb is directly proportional to the resistance. That means if you know the rated resistance of this one and this one, or the resistance of this bulb and this one by using this formula, here we can write resistance is equal to V naught square by P naught. So if you know this resistance, we can find the voltage. Similarly, what is the power consumed here? The power consumed by first bulb, P is equal to, we can write this as P is equal to, as I is constant, instead of P is equal to V square by R, here I can write P is equal to I square R. So power consumed by the first bulb is given by P is equal to I square R. So P1 is equal to I square R1. This is the power consumed by first bulb. P2 is equal to I square R2. So from this you can cancel if you divide these two. Power directly proportional to R. So voltage directly proportional to R, power directly proportional to R. So what is the conclusion here? Whenever bulbs are connected in series, the voltage and power consumed will be more for the bulb having more resistance. So PD, potential difference between the two ends of the bulb, and power consumed are more for the bulb having high resistance. If resistance is high, that bulb will consume more power and that bulb will get more potential difference between two ends. Similarly, if the bulbs are connected in parallel, now let me draw one diagram. This is P1 and this is P2, and these two are connected to a voltage source here, a potential V. Now, in series combination, current is same. In parallel combination, voltage is same across these two and also equal to the voltage of the source. So V is same here. So from this we can write what is the power consumed by first bulb. Power P is equal to V square by R1 and power P2 is equal to V square by R2. As V is same for both bulbs, as these two are connected in parallel, so P1 by P2 is equal R2 by R1. So from this we can write P inversely proportional to R. So this is the power consumed, P inversely proportional to R. Here you can see power directly proportional to R in series combination, but power inversely proportional to R in parallel combination. So what is the meaning of this one? Not only this one, what are the currents through the first bulb and what are the currents to the second bulb? I1 is equal to V by R1, I2 is equal to V by R2. As V is constant, here you can write I inversely proportional to R. You can see these two, the power consumed as well as the current passing through a bulb is inversely proportional to the resistance. So from this we can write current through a bulb, that is I, and power consumed, that is P, are inversely proportional to resistance are more for a bulb having less resistance. If resistance of the bulb is less in parallel combination, then that bulb with less resistance will consume more power and more current will pass through this one. In this case, let us say P2 greater than P1. So power consumed is more by the second bulb than the first one. So power consumed is more. From this we can say resistance of the second bulb is less in this case. Here there is a question. 3 similar bulbs are connected in series across a source of EMF, dissipate 10 watts of power in total. What would be the power dissipate if the same bulbs are connected in parallel across the same source of EMF? First, the bulbs are connected in series across a source of EMF E. Now in this total power consumed is 10 watts. So power consumed is given by E square by resistance R. All are similar. So total resistance of this combination will become 3R. So power P is equal to total voltage by total resistance I am drawing. So this is total voltage square by 3R. So this is equal to 10 watts. Let me take it as equation 1 as it is the power consumed in series combination. So let me take it as PS as 10 watts. Now in the second part of this problem, the same bulbs are connected in parallel across the same source of EMF. Now, what is the power consumed in the second case? The power consumed in parallel combination, I am writing PP, power consumed in parallel combination is given by E square by, this is R, this is R, this is R, together this will become R by 3. So this is R by 3. So this is 3 E square by R. This is the new power consumed in parallel combination. E square by 3R is equal to 10. E square by R is equal to 13. So here you can write E square by R as 13. So power consumed in parallel combination of the bulbs is given by 3 into E square by R, which is equal to 30. So it will consume 90 watts power. Problem. To heat a given mass of water from 20 degrees to 60 degrees, heater 1 takes a time T1 seconds, whereas heater 2 takes a time T2 seconds here. So these are the seconds in seconds. Find the time taken by series combination of these two heaters and parallel combination of these two heaters. This was the problem which was given so many times in competitive exams. Now first let me take the first heater. So I am going to take heater 1. So heater has some resistance which is connected to a source of EMF. Let me take it as E, and it has some resistance R. So what is the power consumed by resistor here? The power consumed is equal to E square by resistance R1. But this resistor is dissipating heat which is used to increase the temperature of water from 20 to 60. So what is the heat produced here? Power is equal to heat produced per unit time. So I can write this as P1. Let me take this as P1 here. P1 is equal to H by T1. But if you want to find out the heat produced to heat this one, H is the product of power into time. So we can write power is equal to, this H is equal to, what is this power? E square by R into T1. As this EMF is constant, heat required is equal to some constant into T by R1. So first let me write this as E square T1 by R1. This is equation 1. So to heat that given mass of water, we need this much of heat energy, which is equal to the square of the EMF into time taken, which is given as T1 by resistance of this resistor. Now what about this for heater 2? Heater 2. So let me use one more resistor having resistance R2 connect to the same source of EMF. Now the power consumed by the second heater is given by E square by R2. So what is the heat required to increase the temperature from 20 to 60 for a given mass of gas, water? So this is given by heat is equal to power into the time taken. So this is a power P2 T2. P is equal to E square by R2 into T2. So here also H is equal to E square by R2 T2. So this much heat is required to increase the temperature from 20 to 60 degrees. But in both cases for these two heaters, we are going to take the same quantity of water and the increase in temperature is always from 20 to 60. So from this, this heat required to increase temperature and this heat required to increase temperature must be same. So if we equal these two equations, we can write E square by R1 T1 is equal E square by R2 T2. E square get cancelled. So from this we can write T1 by T2 is equal to R1 by R2, or R1 by R2 is equal to, this will be T1 by T2. So we got a relation between ratio of resistance of these two resistors and the time taken by these two to heat the water from 20 to 60. Now in the second case, in the second part of this problem, actually this one, when these are connected in series, so I am going to connect two resistors. The first one R1 and the second one is R2. And these are connected to the same source of EMF E. Now, what is the time taken by this series combination of these two heaters with the same source to heat the water from 20 to 60 degrees? So here, the power consumed is given by, in series combination, the total EMF is E square and the total resistance of this one is R1 plus R2. Now, how much heat is required to increase the temperature from 20 to 60? We know heat required must be equal to E square T1 by R1. So here also how much heat is required? Same thing, E square by total resistance of this combination is R1 plus R2 into, and the total time taken is T series, because now the resistors are connected in series. This heat must be equal to either of these two equations, either this or this. So let me take the first one, E square by R1 T1, you can cancel E square and E square. I need this time taken in series combination. So I can write T series is equal to R1 plus R2 by R1 into T1. So this you can write R1 by R1 will be 1 plus R2 by R1 into T1. What is this R2 by R1? Here we have R1 by R2 as T1 by T2. If you reverse this one, R2 by R1 is equal to T2 by T1. So this equation 1 plus T2 by T1 into T1. If you take LCM here, this is T1. This will become T1 plus T2 into T1. You can cancel these two. So what is the total time taken by this series combination of heater to heat the water from 20 to 16? So in the first part we can write the answer as T series is equal T1 plus T2. So this is the first combination. Now in the second part, if these two heaters are connected in parallel, now this is the second resistor which I am drawing as R2, and the first resistor, let us say this is R1, but these two are connected in parallel now. So I am going to draw a diagram like this, and these are connected to the same source of EMF E. Now what is the power consumed in this case? The power consumed is given by, in parallel combination I am writing PP, the total EMF by the total resistance of this combination, which is given by product of resistance by sum of resistance. So this is R1 R2 by R1 plus R2. So I am going to write R1 R2 by R1 plus R2. This is the total power consumed in parallel combination. But how much heat is required to heat the water from 20 to 60? So heat produced, heat required here is equal to, so heat required is equal to H is equal to E square by, what is the total resistance of this combination? That is R1 R2 by R1 plus R2 into the total time taken in parallel combination T parallel. But how much heat is required to heat this water? Same as this or this. So you can take any one of this equation. This will be given by E square by R1 T1. You can cancel E square and E square. Now I want this T parallel. So T parallel is given by 1 by R1 into T1, and bring this equation to this side. This will become R1 R2 by R1 plus R2. You can cancel R1 here. So T in parallel combination is given by, this will be T1 into, this is R2 by R1 plus R2. So this is R2 by R1 plus R2. Now you can write the same thing in denominator also, as this is T1 into, this is 1 by, this is R1 plus R2 by R2. Now T parallel is going by T1 into, this is 1 by R1 by R2 plus 1, or 1 plus R1 by R2. But what is R1 by R2? R1 by R2 is nothing but T1 by T2. Now you can substitute this as T1 into 1 by 1 plus T1 by T2. Now you can write T1 plus T2 in T2. So this will become T parallel is equal to T1 T2 by T1 plus T2. So this is the total time taken by the two heaters to heat the water from 0 degrees to 60 degrees in parallel combination, which we can write it as T1 T2 by T1 plus T2. So this is how we can solve this problem. But if you want to solve this problem in a shortcut method, what we can write? Here I got times taken by this one is directly proportional to the resistance. So first we need to find out this relation. After finding this relation, in in series combination, T series is directly proportional to R series. So T series is equal to, what is this R series? R1 plus R2. You can write R1 plus R2 into some constant, or you can write as R1 directly to T1, R2 to T2. So R1 plus R2 will become T1 plus T2. In one step you can write this one after finding the relation between R and T. Similarly, in parallel combination, T directly proportional to R parallel. So T parallel directly proportional to R parallel, that is R1 R2 by 1 plus R2. R1 R2 by R1 plus R2. So T parallel to T1 T2 by T1 plus T2. So within two steps you will get this one and this one. So that is what we got here. T series is T1 plus T2. T parallel is equal to T1 T2 by T1 plus T2, just like R1 plus R2, R1 R2 by 1 plus R2. So when connected in series, what is the total power consumed by them? So let me explain. So first of all, I am taking two bulbs having power rating P0 and one more bulb having power rating P0. As it is second bulb, I am taking P02. This is P01, and voltage rating, both bulbs are having same voltage rating. Now, what is the resistance of the first bulb? Resistance of first bulb R1 is equal, if you know the power and voltage, we know power P is equal to V square by R, and resistance here is given by V0 square by P01. This is the resistance of first bulb. What is the resistance of second bulb? So R2 is equal to V0 square by P02. So this is resistance of second bulb. Now I am going to, initially when they are separated, this is the resistance of this first bulb and this is the resistance of the second bulb. So these are the individual resistors before connecting in series. Now let me join these two in series. So in series, what happens when connected in series? This is the first bulb and this is the second bulb. So this is P01, this is P02, this is V0 and V0, and both are connected in series like this here. Now, what is the total potential of this battery or EMF source EMF? This is a V. Now, what is the current through this one I? So in series combination, we know that same current flows through the first bulb as well as in second bulb. We can write as the current is same, what is the power consumed by first bulb? Power consumed by first bulb. To find out power consumed, let me take P1. Don't confuse between P01 and P1. P0 means rated volt power, this is rated voltage. So this is the new voltage of the source and this is the power consumed now. So power consumed by the first bulb is given by P1 is equal current to I square into R1. So what is the power consumed by second bulb, which is given by P2 is equal I square R2. As I is same in both bulbs, we can write P1 by P2 is equal R1 by R2 or P directly proportional to R. From this we can write power consumed is directly proportional to R in series combination. Now in this case, if you know the relation, let us say the power rating of this one is greater than this. If power rating of the first bulb is greater than the power rating of the second bulb. If power rating is more for the first bulb, resistance must be less. So we can write R1 less than R2. If we know that if the power rating of first bulb is greater than second bulb, let us say this is 100 watts bulb, this is 60 watts bulb. So from this what we can say, these are the rated powers of these two bulbs. Here P01 is greater than P02. So automatically resistance of this bulb must be less than this resistance. That means it will have more resistance, that's why less current will flow, less brightness or less power. Now from this, if R1 is directly to power, so we can write P1 less than P2. So bulb having more power rating will consume less power in series combination. So that we have to remember very carefully whenever two bulbs connected in series. Here we can write bulb with high power rating consumes less power in series combination. Why? Because same current has to flow through these two. When same current is flowing, this resistance is less, this resistance is more, because power rating is less, resistance is more. As it is having more resistance and less current has to flow, but both are connected in series, same current has to flow. That's why the power rating of this one is more, but it will consume less current. Why? Because if the current is more than the rated value of this one, this bulb will be damaged. That's why this will consume, high power rating will consume less power here in series combination. Now similarly, let me take two bulbs connected in parallel. So before connection, this is the first bulb rating P01, this is the second bulb having P02. So we can write R1 is equal to V0 square by P01 and R2 is equal to V0 square by P02. So these are the resistance of these two bulbs before connection. Now in parallel combination, after connecting in parallel combination, this is the first bulb, this is the second bulb, which are connected in parallel to this source of EMF V. So now from this will be P01, this is P02. When these two are connected in parallel to the same source of potential V, now we know that the potential across these two bulbs will be same. So what is the power consumed by first bulb and what is the power consumed by the second bulb? Power consumed by first bulb, which is given by P1 is equal, as we are finding the power consumed in parallel combination, potential here is V, here V, we can write V square by R1, power consumed by second bulb will be P2 is equal V square by R2. Here I found that as the current is same in these two cases, P directly proportional to R. P1 by P2 is equal to R1 by R2. P directly proportional to R. But in this case, the voltages are same. P inversely proportional to R. So from these two we can write P1 by P2 is equal to R2 by R1. So their power consumed is directly proportional to the resistance. Here power consumed is inversely proportional to the resistance. Now let me take the same case. If the power rating of the first bulb is greater than the second bulb, if P01 greater than P02, rating of the first bulb is more than the second one. So here, as we know that P inversely proportional to resistance, as P01 greater than P02, what about the resistance? P01 is greater, R1 should be less, R1 should be less than R2, but R inversely proportional to the power consumed here. So P1 should be greater than P2. You can see the initial power rating of the first bulb is greater than the second bulb. Power consumed of first bulb is greater than the second one. That means in parallel combination, bulb with high power rating, more power rating, high power rating consumes more power in parallel combination. So now if you connect this 100 watts bulb here, in example 60 watts bulb here, 100 watt bulb will consume more power than the 60 watt bulb only in case of parallel combination. That's why in our houses we will connect all these bulbs in parallel combination, so that here one more advantage is, now in series combination, let us say this bulb is damaged, that means it will be in open circuit, it is not taking any current. So whatever the current that is coming here will not travel to this bulb, even this bulb will not work. That means in any series combination, in decorative bulbs, so generally bulbs are connected in series in functions and weddings. Now if one of the bulb is damaged, no current will flow through the other bulbs and all the bulbs will not work at all. But in parallel combination, let us say this bulb is damaged due to some problem and the current can flow through the second bulb or the third bulb or the fourth bulb without any problem. That's why it is better to connect these bulbs in parallel combination, where the bulb with high power rating will consume more power, bulb with low power rating will consume less power. In series combination, the actual power consumed by first bulb is this much, the actual power consumed by second bulb is this much. What is the total power consumed in series combination? So total power consumed is given by P1 plus P2. So how to find this total power consumed? Total square of the potential by total resistance, that is applied voltage V square by resistance of each bulb is R1 plus R2. So in series combination this will become R1 plus R2. Now we know the R1 value, we know the R2 value. So the total power consumed is given by V square by R1 is given by V0 square by P01. V0 square by P01 plus V0 square by P02. So we can write this as, if you take V square in the numerator and if you take V square common, this will become 1 by P01 plus 1 by P02. Now the total power consumed is, this will become V square by V0 square into this denominator, we can write this as 1 by P01 plus 1 by P02. So from this we can write the total power is equal to this V by V0 square, V by V0 square into this, if you take LCM, this is P01, P02 by P01 plus P01 goes up. This will become P01, P02 by P01 plus P02. Now, if the applied voltage is exactly equal to the rated voltage, this is equal to V0, then these two get cancelled. So the total power consumed is it is in the form of R1 R2 R1 plus R2, or if you write this, you can write this as 1 by P is equal to 1 by P naught 1 plus 1 by P naught 2. So this is the expression to find out the total power consumed, or directly you can write P is equal to P naught 1 into P naught 2 by P naught 1 plus P naught 2, and it is easy to remember. In series we got a parallel formula, that means for resistor it is 1 by R1 plus 1 by R2, but for bulbs we will get for series combination this is like this. Now what about the total power consumed in parallel combination? Now in the parallel combination what we can write? The total power consumed is given by V square by R1 R2 by R1 plus R2, R1 R2 by R1 plus R2. So this can also be written as P square by, this is you can write V square into 1 by R1 plus 1 by R2. You can write like this. So the total power is equal to V square into, what is 1 by R? Here we have R1 is this much. 1 by R will be reverse of this one, P naught 1 by V naught square. P naught 1 by V naught square plus P naught 2 by V naught square. So you can write this as V by V naught whole square, and the remaining terms in the bracket will be P naught 1 plus P naught 2. So the total power consumed will be applied voltage by rated voltage whole square, P naught 1 plus P naught 2. If the applied voltage is exactly equal to the rated voltage of any of these two, now these will become 1. So total power consumed is P naught 1 plus P naught 2. Be careful, for resistors in series the total effective resistance is R1 plus R2. But the total power consumed is not P1 plus P2, this will be 1 by P naught 1 plus 1 by P naught 2. Similarly, in parallel combination, the total resistance is R1 R2 R1 plus R2, but the total power consumed will be P naught 1 plus P naught 2.